Hi, I'm Dan Horstman. I'm an undergraduate physics major here at the University of Maryland, and today I'm going to be presenting the rotating chair and bicycle wheel demo. So there's two components to this demo. One is this chair that rotates, and the other is this wheel that also rotates. You see, angular momentum is all about things rotating. So let's get this wheel spinning. All right, so now, if I lift my feet from the ground, I'll be in a state of equilibrium. What will happen if I rotate the wheel, if I flip it over? Do you think I'll rotate to my left? Do you think I'll rotate to my right? Or do you think nothing will happen at all? All right, let's see if your intuition was correct. So as you can see, I start to rotate to my left, which is counterclockwise. So if you guessed that, you were right. Now, let's take a look at the physics behind what's happening here. The reason that I start to rotate is due to the conservation of angular momentum. This wheel here has angular momentum L, and the first thing we're going to need to do is figure out the direction of the angular momentum. To do that, you're going to extend your right hand, and you're going to curl your fingers in the direction that it's rotating. The direction your thumb points is the direction of the angular momentum. So if it was going this way, it would point down. This way, it points up. In the case of our wheel, the angular momentum starts out pointing up. We'll call that the positive direction. When I flip the wheel over, the direction now points down, meaning the wheel is now contributing negative L angular momentum to the system. The conservation of angular momentum tells us that the total angular momentum of the system must stay the same unless acted on by an outside force. So it is this change in the direction of the angular momentum that causes the chair to rotate when we flip the wheel over. So this isn't just something we do in a physics demo. This actually has a practical application. We can use this same technique to orient satellites in orbit. In fact, one of the orientation systems on the Hubble Space Telescope utilizes 4 disks, each about 2 feet in diameter, controlled by a computer that rotates them to manipulate its angular momentum. Since the Hubble is weightless in orbit, this lets us aim the telescope. Well, there you have it, the conservation of angular momentum. What do you say we take a look at this thing one more time? See you around.